Section 5.6 is indeterminate forms and L'Hopital's rule. In this section, we're going to learn how to deal with limits where direct substitution yields 0 over 0 or plus or minus infinity over plus or minus infinity, which are indeterminate forms. But before we start with indeterminate forms and L'Hopital's rule, let's talk about evaluating the definite integral if we're given the integral from -1 to 1 of 1 over x squared, because we want to know why is it that we're learning L'Hopital's rule. So let's say I wanted to evaluate this definite integral. Well, you might say, well, this is easy. I know that this guy here is basic form, so I could rewrite it with a negative exponent, and I'd have the definite integral from -1 to 1 of x to the -2nd dx. Evaluating this, I'd get negative x to the negative first, evaluated from -1 to 1. Writing it without a negative exponent, it would be -1 over x, evaluated from -1 to 1. Plugging in the limits of integration, it'd be -1 over 1, minus the negative is plus 1 over -1, and so we might say, hey, you know what? This definite integral here is equal to -2. Well, this is absolutely wrong. Why is it not correct? Because if we think about the function itself, 1 over x squared, if we were to think just about its graph, it looks like this. Now recall, the definite integral gives you area under a curve. So from -1 to 1, the problem with this function is that it's not bounded. So it is unbounded from -1 to 1. So we can't find the area under the curve. This particular definite integral is called an improper integral. And we're going to look more at improper integrals in section 8.8. But before we get to improper integrals, we're going to learn L'Hopital's rule, because sometimes we're going to need to use L'Hopital's rule to help us evaluate those improper integrals. So let's recall what we learned in Calculus 1. In Calculus 1, we dealt with two different types of indeterminate form, those that are 0 over 0 and plus or minus infinity over plus or minus infinity. If we had, let's say, the following three limits in Calculus 1, well, we know that anytime we deal with limits, the first thing we do is direct substitution. So here I'd substitute a 1 in place of my x's, and I'd have 1 minus 1 over 1 squared minus 1, which is 0 over 0. Now in Calculus 1, what we were told to do is, well, if you end up with 0 over 0, go back to this guy, factor and reduce, then try the limit again. So we'd say the limit as x goes to 1, and then the numerator cannot be factored, but the denominator is the difference of squares, and we would get x minus 1 times x plus 1. Then I would cancel out that common factor of x minus 1, and this is really just the limit as x goes to 1 of 1 over x plus 1. Then we would do direct substitution again, plug in a 1, and we'd get that the limit was equal to a half. For number 2, we'd do the exact same thing. We'd start by just plugging in a 0, and we'd have the sign of 0 over 0, but that's 0 over 0. Well, there wasn't anything really that I could do here for the sign of x over x in terms of algebra or trig, but in Calculus 1, we used the squeeze theorem to show that the limit as theta goes to 0 of the sine of theta over theta was equal to 1. This was this special limit that we talked about in Calculus 1. Well, because of this special limit, we can say that the limit as x goes to 0 of the sine of x over x is equal to 1, because instead of thetas, we're just an x. Number 3 was a limit at infinity. And limits at infinity, what we were really looking at were those leading terms. So the leading term in the numerator is 5x squared, because that's the term with the highest exponent. And the leading term in the denominator was 3x squared, again because that's the term with the highest exponent. So we could rewrite this limit as the limit as x goes to infinity of 5x squared over 3x squared, because those are the only things that really matter there. And if you think about plugging infinity in place of the x's here, you were going to get infinity over infinity. For these, when we were doing limits at infinity, we looked at those leading terms, and then we reduced what we could in terms of our x's. Well, in this particular problem, the x squareds would cancel, and then we'd have the limit as x goes to infinity of just 5 over 3, and we get that our answer here is 5/3. So we dealt with all three of these in Calculus 1. L'Hopital's rule gives us a different method for dealing with these three problems. So let's look at what L'Hopital's rule is, and then we'll do examples 1 through 3 again. L'Hopital's rule says let f and g be continuous functions that are differentiable on an open interval ab containing c except at possibly c itself. So this part right here, containing c except at possibly c itself, remember all that meant was that you didn't need to be defined at c for your limit to exist. Limits don't depend on the function value. Remember, they tell you what happens close to that value. So f and g are both functions that are differentiable on that open interval containing c except at possibly c itself. Then we're going to assume that g prime of c doesn't equal 0 for all the x's in that interval except for possibly at c itself. That's okay. Then L'Hopital's rule will state the following. If the limit as x approaches c of f of x over g of x, when you do direct substitution, gives you 0 over 0, or it gives you plus or minus infinity over plus or minus infinity, where c, the number that you're approaching, is any real number or positive or negative infinity, then that limit, the limit as x approaches c of f of x over g of x, is equal to the limit as x approaches c of the derivative of f of x divided by the derivative of g of x, provided the limit exists. What L'Hopital's rule is saying is that if you end up with indeterminate form 0 over 0 or infinity over infinity, that the limit as x approaches c of that function is equal to the limit as x approaches c of the derivative of the numerator divided by the derivative of the denominator. Let's do examples 1 through 3 again, this time using L'Hopital's rule. We know that for number 1, direct substitution here would just give us 0 over 0 because we've already done this. Well, L'Hopital's rule says if that happens, if you have indeterminate form 0 over 0, that what you need to do is take the derivative of the numerator. Well, what is the derivative of x minus 1? Well, it's 1. Then take the derivative of the denominator. Well, what's the derivative of x squared minus 1? 2x. After you take the derivative of the numerator and the denominator, then try taking the limit again. Well, let's do direct substitution again. So I'd have 1 over 2 times 1, or a half. Notice this is exactly the same thing that we got using the methods we learned in Calculus 1. Number 2, remember direct substitution yielded 0 over 0. Therefore, L'Hopital's rule applies because that's indeterminate form, and L'Hopital's rule says take the derivative of the numerator. So we take the derivative of the sine of x and we get cosine of x. Take the derivative of the denominator. We take the derivative of the denominator x and we get 1. And then we take the limit again. Well, I don't need that over 1, so this is just the limit as x goes to 0 of the cosine of x. Well, that's going to be the cosine of 0. Well, what's the cosine of 0? Well, the cosine of 0 is equal to 1. Again, notice that this is the exact same answer we got using that limit that we needed to know from Calculus 1. Finally, number 3. Again, we're really only looking at these leading terms, 5x squared and 3x squared. When you're approaching infinity, we know that that's going to be infinity over infinity. So L'Hopital's rule applies. L'Hopital says, take the limit as x goes to infinity of the derivative of the numerator. What's the derivative of 5x squared plus 1? Well, that's 10x. And then the derivative of the denominator. Well, what's the derivative of 3x squared minus x plus 3? Well, that would be 6x minus 1. Now evaluate the limit again by looking at those leading terms. And guess what? We'd still get infinity over infinity. We can use L'Hopital's rule again. So we take the limit as x goes to infinity of, what is the derivative of the numerator? What's the derivative of 10x? Well, that's just 10. What's the derivative of the denominator? Well, the derivative of 6x minus 1 is just 6. Then we take the limit again, and the limit as x goes to infinity of that constant 10/6 is 10 over 6, and that reduces to 5/3. Again, notice that's exactly what we got using the methods we learned in Calculus 1. Now, just to let you know, when we're dealing with limits at infinity of a rational function, I prefer the way that we did it in Calculus 1 because usually it's quicker than using L'Hopital's rule. Most of the time with limits at infinity, you're going to need repeated uses of L'Hopital's rule.